like. Um, it's been.
Good evening. Good evening. Hello, and welcome to Illuminate Science, an evening discussing big ideas in the world of science. My name is Bernice Tsai, and I'm the Senior Executive Director of Columbia College Alumni Relations and Communications, and I'm also Columbia College Class of '96. I'm delighted to be here to introduce this evening's program. Most of us in this room went to Columbia, and aside from the extraordinary time that we spent on campus and in the city of New York, another shared experience that we have was being challenged by exciting ideas, being astonished, and learning incredible things together. Tonight is going to be another example of how that sense of discovery can bring us together as Columbians. I was an English major in college, but I would say that over time I gravitate more and more to articles in newspapers or hardcovers in bookstores that talk about great ideas in science, the mapping of the human brain, the impact of pollution on our oceans, the fantastic ways that we're extending lives through medicine. These are just some of the ways that science is impacting our world and why it's such an important part of all of our lives. Tonight is the result of a partnership across the Columbia community, the SoCal Alumni Club, the Columbia Alumni Association, the Columbia College Alumni Association, and the faculty of the Columbia Science Initiative. I just want to spend a second talking about the Science Initiative, which is a new initiative at the university, which is trying to place greater focus on the work of our scientists, our faculty members, as well as our students. And I encourage you to learn more about this initiative. We have brought materials with us tonight, so you can take a look at those. And then, of course, at any time, please come back to Morningside Heights and learn more with us there. Tonight we have a very special program in a number of ways. I'd like to give a special shout out to Donna McPhee, Vice President of University Alumni Relations, and several members of her team who support the Columbia Alumni Association. I also want to give a special welcome. I believe that we have a few admitted members of the class of 2018 who I hope to see in Morningside Heights this fall. If you're here, please stand up. Don't be shy. Congratulations. Welcome. And I want to say another thanks to the SoCal Alumni Club members. If you are here, if members of that club, please stand so we can recognize you. Thank you for your support. And we'll be hearing from the club president, Ann Kim, later tonight. So I also want to mention that this program tonight is being live streamed, so welcome to those of you who are joining us around the country or around the world. We will be live tweeting, so please make sure to send in any questions or any comments on of what you think about the program. You can join us at #IlluminateScience, and we welcome lots of input and lots of conversation. Now, let me tell you a little bit about our speakers. So we have an amazing opportunity tonight to hear from Brian Greene, who is an esteemed Columbia faculty member. Brian is a mathematician, physicist, and exuberant teacher who, through his work as a researcher and educator, has perhaps done more than anyone to spread understanding of contemporary physics, topics like string theory, the multiverse, the Big Bang, relativity, and many others. His books, like Fabric of the Cosmos and The Elegant Universe, and now also the World Science Festival, television programs like NOVA, and now a new online platform, World Science U, which was co-founded by Tracy Day, who's also here with us. These ideas take the most challenging and fascinating science out of the lab, out of the lecture halls, and bring them to the minds, eyes, and imaginations of general audiences everywhere. So tonight, we'll be hearing a little bit more about both the science and also the new ways of reaching the curious and the uninitiated. To converse with Brian, I'm delighted to introduce my fellow Columbia College graduate, Gideon Yago, a writer, reporter, and LA resident. Gideon may be known to many of you. He graduated from the college in 2000, and he began his career making documentaries and doing news programming for MTV, for which he was awarded an Emmy, a Peabody, and an Edward R. Murrow Prize. His work has appeared on CBS News, CNN, NPR's This American Life, and HBO. He's currently a writer on WGN America's Manhattan, a series on the making of the atomic bomb, which will be premiering July 13th, so we can all look forward to that. And I want to thank you all so much for being here and ask you to join me in welcoming Brian Greene and Gideon Yago.
Hi, everyone. Thank you to Bernice, and thank you to the Columbia Alumni Association. As mentioned, my name is Gideon Yago. I will be your fake Dick Cavett for the evening, and I am very happy to be here because I think one of the things, once you leave Columbia, that sometimes you don't get a chance to experience are different points of view and different insights from what you do in your day-to-day life. And fortunately with us here tonight is Dr. Brian Greene to have a discussion about some of the breakthroughs in science and some of the work he does and how and why he does it. I wanted to start up our conversation with a little bit of some of the scientific breakthroughs that have been taking place. So on March 22nd, scientists who are working with the BICEP-2 satellite in the South Pole announced what was being hailed as one of the biggest breakthroughs in physics in the last 20 years, which was, and stop me where I get this wrong because I'm pretty sure I'm going to, a recording of gravitational waves dating back to the origins of the universe. And I was wondering if you might be able to shed some light on why that has been such a significant discovery and what it means now for the scientific community and for those of us at large.
Yeah, no, that was a pretty good summary of what happened.
Okay.
The BICEP, the BICEP telescope is down at the South Pole, and for 3 years it's been staring at a patch of the southern polar sky, trying to measure features of what's known as the microwave background radiation, which is heat left over from the Big Bang itself, and a theory that has been on the table since the early 1980s called the inflationary theory of cosmology, which says that the universe underwent a rapid swelling in a tiny fraction of a second, which was what the bang was. And this theory, which we've been trying to verify since the 1980s, says that as space underwent this rapid stretching, little vibrations in the fabric of space itself should be stretched out, and as they stretch out, they become longer ripples in the fabric of space-time, and those longer ripples would leave an imprint on this heat left over from the Big Bang. It would polarize the light. So the way you have polarized sunglasses that only allow light that's vibrating in one direction or another to pass through the lens, which is why the sunglasses work. Similarly, the light that's been affected by these ripples in space would be polarized, and they've been trying to measure that polarization, which would show up as a swirling pattern in the heat. And the claim was that they have now seen that swirling pattern. And if it's true, and that is still a big if, so if these results stand, they will go a long way toward giving confidence that this inflationary theory is correct.
And what world does it create after, if it is proven true? Where does science go from there? Where does physics go from there?
Well, and I need to underscore, it really is a big if.
Right.
So we do have to underscore that repeatedly. So if these results are confirmed, some people will interpret it as the true smoking gun of this inflationary theory of cosmology, which would suggest that we will have pushed our understanding of the origin of the universe way back to a tiny, tiny, tiny fraction of a second after the beginning, which would be a thrilling prospect for that to be true. Now, even if the theory is not correct, as others will claim there's going to require yet more analysis before you really believe that these observations prove that particular theory. Putting all of that to the side, if these results are true, it means that we will have been able to open a window onto the earliest moments of the universe. Forget about theory. We are now seeing things that took place at, say, a billionth of a billionth of a billionth of a billionth of a second after the beginning. And that is amazing that we can sit here on planet Earth and look out into space and perhaps, if these ideas are correct, see what happened in that tiniest moment after creation. That's an amazing thing.
How long do you think it was after the discovery of general relativity before you reached a tipping point in mass culture where suddenly the new world that had opened was kind of occupied by the rank and file, where people really truly understood the significance of the discoveries at that time?
It's not clear we've reached that point yet. Right.
So like 50, 60 years in the future?
You know, but what I will say is the case, Einstein as a singular character entered popular culture in a very big way quickly after 1919. So 1919 was the year that observations of distant stars made visible by the solar eclipse of 1919 allowed Einstein's general theory of relativity to undergo its first rigorous test. Because Einstein's theory says that space and time can warp and curve, which would mean that distant starlight would curve as it passes by the sun. Usually we can't see that starlight because the sun overwhelms the light from distant stars. We don't see stars during the day. But when the moon blocks out the sunlight, all of a sudden the distant stars become visible, and you can measure whether or not the light that they emit that grazes by the sun on the way toward Earth gets bent. And that experiment was first carried out in 1919, and indeed it showed that Einstein's theory was borne out. In fact, there's a famous story that Einstein received a telegram telling him that the observations had confirmed his theory, and someone asked, Dr. Einstein, what would you have said if the observations did not confirm your theory? He said, well, I would have been sorry for the dear Lord because the theory is correct. You know, so after that moment, the New York Times picked up this result. You know, this big headline, you know, lights all askew in the heavens. You know, Einstein topples, you know, Newton's theory. A little small print, you know, only 12 people in the world understand Einstein's theory. But amazingly, it even says in smaller print, you know, but his publisher was so bold that he put this theory into print. It's like, is it really that bold to put the equations of general relativity into print? I mean, what really could happen from doing that? But yes, I guess it was a bold move. But Einstein then, you know, was seen, you know, with you know, famous movie stars, you know, Charlie Chaplin, you know, great iconic photographs that spread his image around the world. So very quickly it became part of the culture.
Well, now we live in a world where people talk about quantum probability, quantum computing, quantum thinking, quantum spirituality. It's almost become sort of a catch-all adjective.
Hey, I'll tell you, I know you have a real question coming after this, but...
I do, I really do.
But you know, I actually did a little bit of study because since this is like Columbia-centric, I was teaching the Frontiers of Science course, and you know, for my quantum lecture, I wanted to show some of the ways in which this word has been taken over by the culture. And there's this wonderful device called the quantum sleeper that I came upon, where it is this bed.
Randomly, you just get hit by sleep and wake.
Well, it's sort of like this. Well, it's actually different. It's this bed where you actually can close it in on yourself, and it says it'll protect you against, you know, nuclear war, you know, terrorist attack. You know, it's a quantum sleeper. But anyway, so to your real question.
Well, no, to my real question is, I think that, you know, you look at the gap between that discovery and where we are now and kind of the use or abuse or misuse of the word, and the role of scientists along the way in terms of helping society in general grasp the concept. And now with BISTEP 2, the reason that I asked that question was, how long do you think it will be before the significance of these discoveries suddenly becomes day in and day out part of our lives?
Yeah.
And how do we get there?
So I don't think it necessarily becomes day in, day out part of our lives in that sense, but there obviously is now a very short trajectory from a major breakthrough and it getting out there in a way that's fairly accessible and relatively accurate. You know, there was some criticism that's worthy of a separate exploration that the scientists who made this breakthrough that we're talking about, they went right out with a press conference to announce the result, as opposed to the more traditional, which is a slower route. You write the paper, you send it out, it gets peer reviewed, you have to respond to the criticism of the community, which is the more traditional way of doing it. So they had a press conference, and as I think everybody in this room knows, it immediately got picked up. And maybe just see how many people had heard of this breakthrough before we were discussing it here. Right, so it's sort of 80% of the room.
Sure.
How many of you online had heard? Let's just do the poll there, right? They got the red light, so clearly everybody. So that is kind of a wonderful new feature which can be abused, but has the potent impact of allowing people to feel that they're part of the discovery. They don't have to wait 6 or 8 months to hear about it, or to wait for, say, a NOVA program, to do some big exposition of it. These things get out there quickly, and that's an exciting thing for scientists.
I think one of the exciting things for those of us who are not in the sciences is to have our mode of thinking, or have our view of the universe sort of questioned by those who are specialists and pioneers in this field. We were talking a little bit earlier in the green room about the need to have an interpersonal dynamic in really understanding some of these more theoretical concepts. I was wondering if you could, I asked you not to answer that question while we were there, but I was hoping that maybe you could answer it now as to why you feel at a certain point, in theory, you need someone to guide you further down the line.
Well, and again, just to give a little bit of context, when we were initially talking about that question in the green room, it was the question of, with all of the move to digital education, to what extent does the faculty member matter, even in the digital space? And my thinking on that is that the faculty member plays a vital role. I mean, if you look, for instance, just as one data point, at those scientists who, say, won the Nobel Prize, a significant fraction of them, I don't remember the exact number, but it's large, a significant fraction had a Nobel Prize winner as their advisor, right? So having somebody who has great insight into not just the technical aspects of these ideas, not just the big ideas, but someone who can take you by the hand and lead you through the intricacies of these abstract ideas, I think that's a vital part of the education, a vital part of absorbing the ideas in a deeper way, so that you can't just, answer the questions on the exam, but you really have an intuition about how they work. And I don't think, obviously you can get that intuition in many different ways, but I think the most efficient and effective way of doing that is to have a guide who's really right there with you. You can see that person and feel that there's a trust between the two of you, and that allows you to get through those difficult moments as you're trying to understand quantum mechanics or general relativity or even special relativity. These ideas are hard because they're so unfamiliar. And having a familiar hand that takes you through it, I think, makes the learning process all that much more effective and efficient.
Let's talk about some of the notes that you hit, or that you try to hit, when you do that in your own work. I'd like to read you a quote, actually, from something that you wrote.
Always frightening.
No. It says, how do you engage... Oh, excuse me.
That was what you wrote.
Yeah, that was what I wrote. There we go.
It sounded like Gideon.
Allow me, just give me one moment. You said, we rob science education of life when we focus solely on results and seek to train students to solve problems and recite facts without a commensurate emphasis on transporting them out beyond the stars. Is it only a sense of awe or only a sense of wonder with which you can communicate some of these higher concepts in science?
No. So that quote, I don't remember where it came from.
You had written an op-ed.
It does sound familiar, though.
Yeah,
which
we
is
all
good.
know exactly.
But I'm pretty sure what I was referring to there, especially if it was an op-ed, is that when you're talking about younger students and you want to keep them interested in science. We always talk about get them interested in science. No, 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 no. They start interested in science when they're 3 or 4 or 5, right? They smash things together. They want to know how things work. They're constantly asking why this, why that. They start as scientists. If you want to keep that interest alive, you need to keep the big ideas front and center, as opposed to just, can you solve that equation or remember the parts of the cell or balance that chemical reaction? All vital things. I'm not saying throw away the details. I am absolutely 100% behind the rigor of science and science education. But to keep the student interested in the details, you've got to show them why the details matter. So at that level, the awe and wonder is important. But when you go further on in the educational process, when you're talking, say, to the undergraduate science major or the graduate student, they're already there, right? You don't need to keep them excited or interested. They've got the motivation. Then when we're talking about how do you train them in the most effective way, then it relates to the thing that we were talking about earlier. Having somebody who can be with them for that journey is a vital part of the education.
When you do your books and your lectures, or you look to do albums or polydisciplinary performances, where do you start? What's the initial idea that you seek to connect with?
You know, it depends on the project, you know, enormously. But just to be concrete, you know, there's this project that we did actually with the World Science Festival, so Tracy here produced a project called Icarus at the Edge of Time, which was a kind of an unusual melding together of, you know, story, science, music, and film. So this is just a 30-second background, is a story that I wrote about sort of a reimagining in a futuristic sense of the myth of Icarus. The boy doesn't have wax wings, and against his father's advice, fly near the sun. That's original, of course. In this case, the father says, don't take your rocket ship and go to a black hole. And nevertheless, this futuristic Icarus does that. And unlike the original, where, of course, the wax wings melt and the boy dies, in this version, it's Einstein's general relativity that dictates how the story unfolds. The boy goes to a black hole, hangs out there for just a few hours, but the real physics that Einstein taught us is that time slows down near the edge of a black hole. So even though it was just a few hours for him, when he comes back to show his dad what he's done, he quickly learns that it's 10,000 years into the future, and his dad has been dead for 10,000 years. So it's a sort of different version of the story, but one that is driven by science. And in that particular case, that was the key thing for me. I wanted to try to create something where you wouldn't feel someone's lecturing to you about general relativity. You wouldn't feel like someone's, you know, trying to really teach it to you. You just kind of go on an enjoyable story journey, and by virtue of going on that journey, you just kind of absorb the science. That was the point there. And one of the key things, too, was, you know, this started as a book, but then we turned it into this stage performance because music and film are such a great way of going right through to the body. You don't have to sort of go through the head, the thinking, the cognitive part, which is always what we associate with science. I wanted science to kind of penetrate immediately, and having music and film was a vital part of making that happen.
When you talk, though, about film being a way to kind of access people emotionally, you know, through the body, I'm going to quote Aristotle by way of the film mogul Harry Cohn, which is, you either make the audience laugh or you make the audience cry. Blowing the audience's mind and giving them a renewed sense of wonder about the world around them, I mean, that's icing on the cake if you can get there. How would you take the scientific discoveries that you're working on the forefront of in physics, and actually, are there narratives besides just the mythic that you can apply towards daily life?
You can, but let me just go back to that
Sure.
that directive that you mentioned there, because, you know, when the book version of the story came out, and the publisher sent us copies, it was actually dedicated to my son, and my father's no longer living. But my son was, I guess, 5 at the time when the book came, and I didn't want to give him this book, this story, for fear that he would be like, oh, it's another one of Dad's things. He always, makes me read his books. I didn't want it to turn into that kind of a dynamic. So I wanted him to kind of come to the book on his own, so I kind of left the book around the house. Many copies I left,
Subtle,
around
very
the
subtle.
house. And he did find one copy, and he asked my wife to read it to him, and she did. And at the end, he was crying, right? And, some people asked me, well, didn't that make you feel bad that you wrote the story that made your son cry? And he was crying because, the dad is dead at the end of the story. And yeah, at some level, I felt bad, but really I was thrilled. And I was thrilled because if a story based on Einstein's general theory of relativity can make a 5-year-old cry, I think that's a good thing, because science becomes more than, again, just the facts and the figures and the solving the equations. It becomes something where you really think about how it affects your life. So for weeks after my wife reading him the story, my son was asking me questions like, well, like if the black hole was smaller, would the dad still be alive when the boy comes back? Couldn't the boy maybe not have gotten so close to the black hole, and then maybe when he came back it would only be 20 years later and the dad is still alive, there's not 10,000. So he was really trying to think about the ideas driven by this emotional reaction to a story that at its core was scientific.
I think we actually have a clip that we might be able to run
Of the
Icarus.
trailer thing.
Yeah, the trailer of the
okay,
Icarus. If we could possibly load that up so you guys can see a little bit more tangibly what we're talking about. Possibly.
My intention in creating this project was to have a performance piece that would have the same edge of your seat quality as some of the greatest of works, but where the narrative would be driven by science. The emotional center of the piece is the transformation of a boy who's going out in space, who's going to explore a black hole. And I could just sort of hear, roughly in my mind, Philip Glass's music just pounding and driving and pushing this forward.
There we go. And we're back up. Awesome. Thank you. I hope you guys were as moved by that as I was. The science fiction writer Roger Zelazny wrote that if the liberal arts do nothing else, they provide engaging metaphors for the thinking that they displace. Is he right? Does doing this kind of polydisciplinary work actually displace real thinking and real understanding?
I don't think so. I think it can enhance it. I don't think it displaces it. In fact, there are some people who get confused by that kind of thinking. I've definitely had students over the years come to my class and say how excited they are. They want to be a physicist. And in the next breath they say, but I don't really like math. I don't want to do any of the math stuff. I just like the physics that's in your books. And I have to sit them down and explain to them the books are a translation from rigorous mathematical investigations that have to do with how we believe the world works, translating from the mathematics to ordinary language. But the ordinary language version is not what the act of being a physicist is all about. That is the metaphor. That is the translation, but it's not a substitution in any way. And the student version of that kind of scenario that I just described is interesting. It's a teaching moment, a learning moment, but the sad ones are when I get the packet from the guy, and it's almost always a guy, I'm not being a gender, the guy who's been in the basement of his house for 20 years with like the single light bulb, who's been trying to take the ideas of string theory further by, say, reading The Elegant Universe and just trying to press onward. I mean, there was one guy who, I hope he's not watching, but he wrote me this letter how, he's been down in his basement for these years, and it destroyed his marriage, and his kids have, gone, but he felt that he was on the verge, and this was so much more important to him than anything else in his life. And it was all coming from a misunderstanding of metaphor versus the technical mathematical version, which is the only way to push the ideas forward.
Do you ever find yourself in a position where the tail wags the dog and there's things about art or things about culture that help you convey the deeper understanding of whatever the dynamics are that you guys are on the forefront of in the physical work that you do?
No.
No?
Yeah, no, I've never, I've been asked that before, and I've never really been able to come upon an example where some part of the parallel activity, be it in art, be it in writing, so the more literary side of things, has somehow had such a profound back reaction on my thinking about the science that it's driven it in some way. The closest that I could say that I've come to that, as I was, say, writing The Elegant Universe, and constantly thinking about the need to establish in the mind of the reader why it is that we do what we do. Why are we studying string theory and unified theories? And the reason that we'd always told ourselves in the field was we want to get a better understanding of the Big Bang. We want to get a better understanding of black holes, extreme realms of the universe that require a unified theory in order to make progress. And as I continued to describe that to the reader, I realized how little we had really done in actually using the theory to understand cosmology, the Big Bangs, and things of that sort. Now, this was 1999, and my own research then began to shift more towards cosmological applications. And the field since then, and I'm not saying that I shifted it by any means, but many people finally realized there was a great opportunity to start to, in some sense, put the money where our mouth was, to apply these ideas to understand cosmology, and that's where a lot of the research has happened. So for me personally, the shift happened from writing about it, but that's the closest I can come to that version of, say, the tail wagging the dog.
I wanted to read you just a statistic that I think you might, I certainly found disturbing. This is according to a Pew Research poll, which was released last month, and it's on American views of the future in technology. 39% of the American people believe that teleportation is going to be possible within the next 50 years. Does that strike you as high?
No, it is disturbing for people to say that because we can do it now.
I'm sorry, come again?
So it depends on precisely what kind of teleportation you're talking about, but we do teleport individual particles right now
Sure.
from one location to another. Which is, to me, amazing. There's this fella, Anton Zeilinger, who presumably will win the Nobel Prize. If it isn't this year, it'll be in the next few years, where he has a wonderful laboratory set up in the Canary Islands, because he knows where to have a science laboratory. He routinely teleports particles from one island to another, from Tenerife to La Palma. So they're 90 miles apart, and he's making use of a weird feature of quantum mechanics known as quantum entanglement, where he can take a photon and reproduce an exact version of that photon on the distant island using the connection between them that comes from a weird feature of quantum mechanics. Now, presumably the reference there is to teleporting people.
I think it's more in the Star Trek mode.
Right, that's right. And that is something that is so far beyond anything that we can even imagine doing. What we can do for single particles, to try to do it for the number of particles that make up a macroscopic object, be it a human body or an inanimate object, is spectacularly beyond anything that we can imagine doing. So the wonderful thing is that we can, in theory, do it, but in practice, we can really only do it for individual particles.
Just to give you another poll from that, you also have 60% of Americans who seem dubious that there's going to be any kind of long-term space colonization within the same time period. Does that number also strike you as high?
It does seem high there. I think it should be higher. I think there really is a focus, or at least perhaps an unjustified wonderment about setting up human outposts, be it Moon or Mars or whatever. From a research standpoint, we can do so much more with non-human spaceflight.
Sure.
And we've seen this spectacularly with the Mars rovers and other devices that have gone out there. So from the point of view of scientific discovery and research, that's really where the focus should be. But of course, the final frontier is something that grabs us at an emotional level, and it can garner support from a public that finds that emotional side of it so much more compelling. But scientifically, it's not what we should be doing.
Well, I guess the reason that I pull those two data points out
Yeah.
is because I think that they might be indicative of the popular understanding of the sciences in the culture that we live in. On the one hand, there is a much greater belief in the Heisenberg uncertainty principle and the magic of Star Trek. And on the other hand, despite being concrete evidence of an ISS or trips to the moon or whatnot, there's just a profound disbelief that the technological advancements would move us in that direction. Knowing that that is the audience, knowing that that is where an audience sort of comes to with expectations and an understanding of science, how do you capture them?
Well, I think the way you capture any audience, again, on that particular poll, who's being asked, how are the questions being asked? So those are details that I think really do matter. But when it comes to trying to capture a general public that isn't scientifically trained, which presumably is part of what that is evidence of, it is the drama and the narrative of scientific discovery, which I think is the most potent hook. So if you start telling people about the details of a scientific discovery versus telling them the human drama that led up to that discovery, the latter is a far more potent way of getting someone's attention, getting someone interested. I mean, when I go out and talk about science, and I can feel a mood shift in the audience between when I'm telling them some abstract idea about, say, the Big Bang or quantum mechanics, and shifting instead to, so Niels Bohr was trying to figure out how the atomic, when you bring in a human being and their own journey, people are far more willing to go with you into abstract ideas. Again, it's really reflective of what we were talking about earlier. If there's a human person, if there's a human being that is really greasing the rails. So I think that is the vital element that needs to happen. And what we do at the World Science Festival, just because, Tracy is here, it is all about creating scientific programs for a live audience where you can find that narrative arc such that the science is not suppressed, not diluted, but it is wrapped around a storyline that keeps you on the edge of your seat. I mean, it's what you do, right? But the only difference, well, so your goal is, right? Your goal, presumably, is if you can get someone watching your television program at the edge of your seat, you have succeeded, presumably. Absolutely. But if you can do that with also wrapping in the scientific idea that you want to communicate, then you've got a very powerful package.
But don't tell anyone, because if they know, then I'll never work in Hollywood again. I do believe we have some video of the World Science Festival. Shall we try it again?
Video
together?
or audio?
Hi, I'm Brian Greene. I'm excited to announce that I'm teaching 2 new courses on Einstein's special theory of relativity. Where am I teaching them? Anywhere and everywhere, because they're online. Who are they for? For you, for your friend, for your neighbor, for anyone who has a thirst for knowledge. How much does it cost? Nothing. To learn about one of the most exciting discoveries of the last 100 years, all you have to do is sign up. I first learned about special relativity about 35 years ago. But even today, it still blows my mind. I mean, Einstein discovered that space and time have weird, unexpected features. Time can slow down or speed up. Space can stretch or compress. And then there's the power of E equals mc squared. And look, if math is not your thing, that's cool. Sign up for my short course, Space, Time, and Einstein, where I'll explain these ideas with animations and interactive demonstrations. But if you want to go deeper, sign up for my university-level course on special relativity, as we'll use equations, a lot of equations, to grapple with space and time, matter and energy. So join me online, and together we'll zip through the universe near the speed of light.
Nice. Very, very nice. An opportunity to keep the conversation going and interact yourselves, those of you here in the audience and who are watching online. Before we go to and open up the conversation for questions from the audience and questions from online, I wanted to read you one quote and perhaps ask you a question after. I have a friend, quote unquote, who is an artist who has sometimes taken a view which I don't agree with. He'll hold up a flower and say, you see, I as an artist can see how beautiful this thing is, but you as a scientist take it apart and it just becomes this dumb thing. And I think he's kind of nutty. First of all, the beauty that he sees is available to other people and to me too. But I believe, although I may not quite be as refined, hypothetically, as he is, that I can appreciate the beauty of the flower. At the same time, I see much more about the flower than he sees. I can imagine the cells in there, the complicated actions, which also have beauty. There's not just the beauty at this dimension at 1 centimeter, but even on a smaller level. It adds a question it adds all kinds of interesting questions with science knowledge, adding to the excitement and the mystery and the awe in art. That was Richard Feynman in 1993. It's not really a question so much as an opportunity to see you do mental battle with the ghost of Richard Feynman. Do you feel as though he is onto something that really through the sciences you can truly, only through the sciences, can you truly understand and appreciate the aesthetic value in anything?
Well, first of all, I should say that's a quote that I've used about 10,000 times. So it is one that resonates with me greatly. I think if you push it too far, if you say that the only way that you can get the full enjoyment, the full experience of something is through the science. No, I don't think that's the case. I think that it gives you a different kind of experience. In some ways, a richer one, because again, I do think that scientists can appreciate the beauty of the rose or anything else just as any other human can. And indeed, if it adds to your experience to look deeper and see the cells and understand why the rose is red by virtue of the interactions of the particles, or why it has the aroma that it does, again, because of the chemical reactions that are taking place. In some cases, that can add to the experience. So in those cases, I think the scientist is able to go more deeply, but it's really a matter of, for the scientist, a matter of choice. There are certain circumstances where I think peeling it apart doesn't necessarily add to the experience. I think Walt Whitman provides a nice counterbalance to the Richard Feynman quote, right? The poem. Somebody here, no doubt, can recite it to us. You know, when I heard the learned astronomer, right? You know that poem. I think anybody know that poem? I think no one knows that poem.
Come on, Bernice, you were the English major.
I thought you guys had to take the core curriculum, you know, and
the gauntlet is thrown.
yeah, right. So you know that poem, which I cannot recite, but you know it's about a student who is in a lecture on astronomy and describes how he's being told about all the structures out there and the charts and the numbers and the equations, and how he starts to feel kind of sick and kind of leaves the lecture hall, quietly goes out the back and just looks up in silent wonderment at the stars, right? So I don't think it's the case that it's always a matter of overlaying science to really capture the deep beauty, but it's nice and wonderful when you have the option of doing that, and science provides you that option.
I hope all of you have gotten a little bit of that option here this evening. I'd like to open up the floor to questions both here in the audience and online. For those of you who have questions for Brian here in the audience, all I ask is that you raise your hand and allow one of our hardworking mic jockeys, mic people, mic wranglers, to get to you, and then we'll be taking some questions from online as well. First hand I saw went to the gentleman in the gray.
Hi, can you please just explain the photon thing about teleportation and how that actually works, and what the leap of scientific knowledge needs to be to go from that to sort of what the popular imagination is of that?
Yeah. So the full answer would require you, and you're welcome to come to my quantum mechanics undergraduate course, but just to give you a feel for what it's about. One of the weirdest characteristics of quantum mechanics, which was revealed back in the 1930s, so now a long time ago, is that you can have a particle over here and a particle over there, and you can set these particles up in such a way that if you do an experiment on one, it has an effect on the other, regardless of how far apart the particles are. So just to give you a concrete example, particles all have a quality known as spin. The details don't matter, but basically a particle can spin this way, which we call spinning up, or that way, which we call spinning down. So a particle can spin up or spin down, but the weirdness of quantum mechanics is a particle can be in a mixture of spinning up and down at the same time, right? Now, if you have two particles, imagine them both in this funny mixture spinning up and spinning down at the same time. Now, what quantum theory says is if you measure one particle over here, it will always snap to attention and either be up or down when you look at it. But what about its partner far away? Imagine this particle's in New York. This one's here in Los Angeles. So you got these particles doing this. Someone measures the particle in New York. It snaps to attention and spins up. The math says that the one in LA at that moment will snap to attention and spin down, even though you didn't do anything to it. All you did was measure its partner over here in New York. Einstein called that spooky, right? Spooky action at a distance. So these two particles, even though they're far apart, they somehow in a quantum mechanical way talk to each other. Now, how can you leverage that into teleportation? Well, if there's something I want to teleport, I can bring it next to this particle in New York, allow them to commingle. Through their commingling, that's sort of like an experiment, properties of the particle I want to teleport get imprinted on the particle in Los Angeles. And then, with a little extra detail, and that's where quantum mechanics, the math comes into the story, I can manipulate this particle to make it an exact copy of the particle that I wanted to teleport. And weirdly, the particle that I wanted to teleport, because it commingled, it gets affected, it gets changed. So the original no longer even exists. So the only version of the original is this one in Los Angeles. So in some sense, I took the particle from New York and I made it appear in Los Angeles. I have teleported it. That's the essential idea. And that's one particle. Your question was, what would it take to do many particles? Well, we'd have to have a huge number of these entangled particles and be able to bring, say, the human being and have the human being commingle with this collection of particles that are entangled with the ones in LA and somehow be able to measure every single particle in the human being, how it commingles with this huge number of particles in the raw material, and then somehow be able to use that information to manipulate a huge number of particles in Los Angeles. It's the huge number problem that gets in the way of doing it. But for individual particles, we can do it.
You guys will have to excuse me because everything I know about life is now wrong. I'll take the gentleman in the navy jacket.
Thanks for translating these incredibly complicated and esoteric concepts to us mere mortals. And thanks for coming out here. I was wondering if you could tell us the significance of the Higgs boson discovery at CERN recently.
Yep. Yeah, so this is a wonderful example of what we theorists aspire toward, which is an idea was thought of, invented, discovered in the early 1960s by Peter Higgs and a variety of other people at roughly the same time to try to answer a puzzle that was at that time unresolved, which is how do particles get mass? How do they get heft, right? What is heft? Heft is, the resistance an object can give to being sped up or slowed down, right? So as I try to speed, I feel that resistance, and that's his mass, his heft. But when it comes to individual particles like electrons and quarks, where does their heft come from? No one had an answer. But Peter Higgs had this idea that maybe space was filled with a substance, sort of like a molasses-like substance, invisible, we don't see it. But when particles like electrons try to speed up or slow down, as you push on an electron, it kind of interacts with this molasses like a pebble. If you drop it into a bucket of molasses, it feels that resistance. And it's that resistance that the electron feels as it talks to this molasses, which is where its mass comes from. That field is called the Higgs field. It was a hypothetical idea. At first, no one believed it. But then people warmed to the idea. And I have to say, by the time I learned about it in 1986, as a graduate student, the professor teaching us spoke about it with such certainty that I thought it was a confirmed idea. But it was still just hypothetical. How would you go from hypothetical to real, from mathematics to reality? Well, you build this big machine called the Large Hadron Collider in Geneva, where protons go around this machine billions of times a second. They slam into each other, these protons, and the math says that if they slam in the right way, they'll jiggle the molasses. And in fact, they'll jiggle the molasses enough so a little fleck will get knocked off. And that little piece that gets knocked off is called the Higgs particle. So people were looking for that little fleck, that little speck of the Higgs field, the Higgs particle. And July 4th, 2012, in order to sort of step on America's independence celebration, it was announced in Geneva that this particle had been found. And then through subsequent observations, great confidence was finally achieved that indeed the Higgs particle had been found. So this purely mathematical idea from the 60s is now shown to be relevant to the world. This is how the world works. So we are all immersed in a bath of Higgs field, and the heft of at least the fundamental constituents comes from their interactions with this cosmic molasses that fills every nook and cranny of space.
To the lady in the white dress, please. Yeah. Sorry about that. Might be it. If you could just pass that down, please. Thank you.
Sure. Thank you very much. My question is, you mentioned 35 years ago you got interested. What role, if any, did Professor Carl Sagan maybe have to do? Because I saw him at Cornell when I was there.
Yeah,
He was
no,
my professor.
certainly. Carl Sagan had a big influence. The idea that science could be brought out to the world in a way that, would send shivers on the spine was not a familiar idea to me as a high school student. But here was this guy doing it and doing it in a way that was effective for a mass culture. So, it's a funny thing because not too long ago, we were clearing out papers and I came upon the essay that I wrote, on my college application. And in there, I was somewhat surprised, somewhat disturbed to find that I've done what was in my essay, right? I mean, I wrote about wanting to do research on gravity and bring the ideas out to a general public. And that general public part of it certainly came from the influence of Carl Sagan. And as it turned out, just a footnote, I started, at Cornell in the 1990s. That's where was my first faculty job, and I decided to leave to go to Columbia. But, Carl Sagan was there. And I really did want to meet him, but I was so intimidated that one day I was jogging and he had a house and he was working on the renovation. I saw him go in. I was like, it's renovation time, so he's probably going to come out pretty soon. So I kind of hung out outside doing my stretching, and then he came out and I didn't say a word, and so I never actually met him.
Perhaps in another universe.
Yeah, exactly. I'm sure it happened.
I'd like to take the gentleman in the blue.
Here's a question that was tweeted in by Ava Starr. She writes, do you think that dark matter could be the gravitational force exerted by a parallel universe that we are unable to otherwise detect?
Well, Ava, that's a very, very good question. I told Ava to write. No, this is completely independent of me. It's certainly possible. So just, again, 20 seconds of background. I think many people are familiar with the fact that we believe there is matter out there in the universe that doesn't give off light. That's dark matter. Why do we believe that? Many reasons, but to be concrete, when we look at how galaxies are spinning, they're spinning so quickly that the outer stars should be flung outwards, sort of like water droplets on a bicycle tire. But why aren't they being flung outwards? Well, there has to be more gravity than we think that's holding those stars together, holding them within the galaxy. How could there be more gravity? There's got to be more stuff out there that we're not seeing. Dark stuff, dark matter. And it is possible, to get to the question, that this dark matter could actually be the gravitational pull of matter that exists in a parallel realm. That is one of the ideas that comes out of certain modern theories like string theory and others. So the reason we don't see the matter is not that it doesn't give off light, but it only gives off light perhaps in that other realm, and the light doesn't travel to our realm. But gravity has this wonderful property that it generally is very difficult to constrain gravity. If there's gravity, it spills out from one realm to another. So if there are parallel realms, sort of like two slices of bread, two universes that each exist in its own slice of space, gravity will almost certainly travel between them. So it could be that the gravity travels between them, giving rise to that extra pull that I was talking about, but light doesn't. And that's why it appears that this gravity is coming from a source that isn't giving off light. No version of that story have I seen that really holds together fully, but it is one that people have written papers about.
Let's take some more questions. From the lady in the red dress, please.
Yes, well, you said the magic word, string theory. So as for most of us, you are Dr. String Theory. So I'd like to hear about the most recent situation regarding string theory. I think there was a little bump in the road with some of the discoveries from the Large Hadron Collider. So maybe could you fill us in on what's the latest?
What's the latest on string theory? Yes, so again, I just feel compelled to give 20 seconds of background. Again, string theory is this approach to build a unified theory of physics that Einstein was looking for but never found. And the full name of string theory is superstring theory, and the super generally refers to something called supersymmetry. And the bump in the road that you're referring to, I wouldn't call it a bump in the road, but the interesting state of affairs is that there was a long shot possibility that supersymmetry, this quality of string theory, might be observed at that machine in Geneva, the Large Hadron Collider. How would you observe that feature of string theory? Well, supersymmetry, to make a long story very short, says that for every known particle, there should be a partner particle. For the electron, there should be a supersymmetric partner called the selectron. For quarks, there should be squarks. For neutrinos, neutrinos. I don't name these things. But for every known particle, there should be a sparticle that hasn't yet been seen. And the expectation is that the reason we haven't seen the partner particles is because they're much heavier than their cousins, than their known cousins. The hope, again, long shot, was that the Large Hadron Collider might be powerful enough to produce the partner particles and thereby reveal that the supersymmetric quality is correct. So far, no sparticles have been found. No evidence for supersymmetry has been found. Now, the reason why I don't consider this a bump in the road is because the scale at which supersymmetry, the energy scale at which it become apparent, is not provided in any of the equations that we know. It could be a little bit above everyday energies. It could be energies accessible to the Large Hadron Collider, or it could be millions and billions of times higher energy still. So it was always just a hope that this machine that we humans could build in the 21st century would be just powerful enough to reveal the supersymmetric quality. That still might happen. The machine will turn back on in 2015. Maybe we'll get lucky, but I would consider that being extraordinarily lucky, again, if that were to happen. So unfortunately, these theories really come into their own at energy scales probably far in excess of the technology that we humans in this century can build.
Let's take a couple more questions before we close down. Gentleman right in front.
Thank you. So I've heard of a particle called a gravitron, which is like related to gravity.
I think the
Kinda like
Gravitron is an exercise machine that you find at the fitness center. It is. It's the one you can do pull-ups, and there's a platform on it. I think you may be referring to the Graviton. Without the, yeah,
sorry,
good.
yeah.
And then we're together. Good. Let's go.
So what is that, and what does it have
Yes.
to do, like, with the no.
Yeah.
Just what is that?
Yeah, no, it's a great question. So the Graviton is a little tiny particle that we believe is the most fundamental microscopic carrier of the gravitational force. Now, what does that mean? So take a more familiar force, electricity and magnetism, the force that we all know about. That force is transmitted by little tiny particles called photons, little particles of light. So I mean, that bright light right now is sending a huge number of photons toward my eye, little packets of the electromagnetic force. They're entering my eye, they're interacting with the retina, and that's giving me the sensation of sight. But it's all coming from the electromagnetic force carried by this little bundle called the photon. Similarly, the gravitational force, a different force, we believe quantum mechanically is transmitted by little bundles of gravity called gravitons. So if these ideas are correct, and we don't know that they are, we might one day be able to isolate this fundamental constituent of gravity. It has not happened yet, but most people believe that if our understanding of quantum mechanics and gravity is correct, that that particle exists.
Two more. Oh, being told right back there.
So Dan Kessler tweets, in a world of radical theories, what current new theory do you think is the most radical?
It's a great question, Dan Kessler.
What current theory is the most radical? Well, I mean, there's so many to choose from. It's like,
Plausible theory.
So, there are many ideas of how our universe might not be the only universe. So there are many multiverse proposals. They do radical violence to our perspective on what reality is in many, many different ways. And there are different flavors of the multiverse out there as well. And each of them has their own distinctive qualities and distinctive impact on the way that we think reality works. Another wild idea is coming from something called the holographic principle, which comes from the study of black holes, which, when you take it to its logical conclusion, suggests that everything we see in the world around us is a kind of holographic projection of fundamental ideas that exist on a thin bounding surface, much the way a familiar hologram is a thin piece of plastic. You illuminate it, and it creates a three-dimensional holographic image. We would be the three-dimensional holographic image of these fundamental laws that reside on a thin surface that surrounds us, perhaps at the boundary of the observable universe. I don't know if that's enough, but those are pretty wild ideas.
One or two more, because I want to eke as much time as I possibly can out of all of you who came down. Let's go way in the back. The gentleman in the yes, the glasses. Trying to play zone.
Hi. You spoke a bit about the influence of fiction writing on your science work, and I just was wondering what you thought were the ethics that a good science fiction writer should take into account. Like, what is the contribution of a fiction writer in the scientific community?
Well, I think there are many kinds of fiction, and I don't think there are any rules, any sort of ethical, structures that someone who's doing, science or science fiction needs to adhere to. But if you ask me what irritates me in fiction, it's when an author sets up a collection of rules that are not, say, compatible with our understanding of the physical world, but I'm willing to buy into those rules, and then out of laziness, at the end of the story, changes those rules in order that some particular final sequence can play itself out. For me personally, if you're going to change the rules of the world, be consistent about it.
Physicist through and through. You did talk about, I just want to dovetail off of that, because prior to this, we talked a little bit about sort of, the works of culture that kind of evoked your interest in the possibilities of science. And you talked about a Star Trek episode called The City on the Edge of Time.
City on the Edge of Forever.
City on the Edge of Forever, excuse me.
Yep.
Would you like to, or I can paraphrase the plot? And
No,
would you like to talk? So essentially, you go to a place, our friends at the Starship Enterprise go to a place where time is not a closed linear place, where things have the potential to happen over and over and over again. And you described that as an aha moment for you. Can you tell me why? And can you tell me in what way does that weird little bit of Star Trek have any bearing on our understanding of the universe that we know?
Well, you have to remember, so Star Trek was the late 60s. Mm-hmm. As a young kid, so I was, 8, 9, 7, 8, 9, I can't remember exactly which season that, but I remember I'd sit and watch those with my dad. And this notion, which is now, I think, quite familiar because Hollywood has taken on time in many plot devices. But the plot there, where these two characters, go back in time, and it's the whole notion: if you can go back in time, can you change anything? And if you can change things, that can wreak havoc with the universe. Seeing those ideas play out in the context of a plot which was, there's always an attempt, I think, in many of the Star Trek episodes to bring some, human emotional context to it. They did a really good job, and that wasn't cheeseball, even to an 8-year-old or whatever I was. It felt like a real emotional story as Kirk had to make a decision to not save this woman that he loved. He loved a woman in every episode, but whatever, and he had to let her die in order that the universe would play itself out in the way that it was meant to. And to see, again, how this scientific idea of time and time travel could have this real potent emotional context was something that had a big impact on me, for sure, especially as a young kid.
I hope that helps as well. Last question, gentleman in the tie with the jacket. Can I ask you to hold on until a mic gets to you so that everyone online can hear you as well?
Taking it out of the world of pure science into the world of religion with, say, a chapter in Ezekiel that has always been problematic for me, and then popular literature, Jules Verne in the 1880s, describing a nuclear submarine, and in Ezekiel, to a non-scientific observer, describing a Harrier jump jet. Do you think that these were insights into people who could transcend usual time, space boundaries? How else could you understand these things, or were they just mere coincidence?
Well, it's probably aliens, right? I mean, I'm sure it's evidence of aliens. I'm not familiar with the passage that you think has some connection to modern technology, but maybe I can give a parallel example, which is, my brother is Hare Krishna devotee, and in many ways we've been interested in the same kinds of ideas: origin of the universe, the fundamental forces at work in the cosmos, but we've approached those questions from a radically different perspective. And through the years, every time we'd make some breakthrough or I'd learn some new thing, that others had discovered, and I would describe it to him, oftentimes the response was, "Oh yeah, we knew that, Vedic text, 18 or 22," and it was an interesting thing, but only later did I press the point a little bit further, and what became clear to me was it was more a resonance of language as opposed to a resonance of real ideas. So we might be talking about vibrating strings in string theory, and like the notion of vibration might have occurred in this particular Vedic text. But that ain't the same idea, just because there's sort of an overlap of the words or the language or the overarching principles involved. Nowhere in any of those texts was the equation, integral d2 sigma, square root of h, h alpha beta, d alpha x mu, d beta x nu, g mu nu of x, right? The fundamental equation of a string moving through a background space-time, I tell you, does not appear in those texts, right? So I think that's what the difference is. If you're looking for just sort of the suggestion, the tip of the iceberg, then I think there are interesting places where you can find similar words and ideas in non-scientific texts or in early, Jules Verne ideas. But if you look any bit under the hood, it's really not what we're talking about in the modern setting. At least I've never seen an example which is convincing that does.
Well, that, I believe, should bring us towards a close. I would like to paraphrase a quote from the great Niels Bohr, which is, if you are confused by the discussion of physics, then only are you beginning to understand it. Thank you so much for coming out. And now to speak on behalf of the Columbia Alumni Association for more events like this and in the future, I'd like to welcome Ann Kim.
I wanted to give a special thanks to Gideon Yago and to Brian Green for taking a very difficult topic and illuminating it through personal stories. And thanks to everyone who's here with us tonight, here in the room and online. And I hope you'll continue to tweet at Illuminate Science tonight and beyond. We'll also post the video online on the CAA website if you're interested in revisiting any of Brian and Gideon's discussion. You can also register on World Science U to take some of the online classes for free. And my name's Ann Kim. I am the president of the Columbia SoCal board, and we represent 5,000 members in Southern California. And a brief note about our club is that we're building the energy of our Columbia networks in Los Angeles and looking to take it to another level with the Columbia Alumni Association support through revised websites and different events. Our next event coming up is on May 15th. We're having a mixer at the Lexington Social House, followed by our film festival on June 19th. So we hope to see you there. I wanted to briefly recognize our board members who are here with us today. We have Joshua Berman, who is the previous president, if you want to stand up. And Russell Glazer, who's our corporate secretary. Anthony Agoni, he's our vice president of Orange County. William Acker, who is also another board member. And Ed Hoffman. And Ed Hakeem. And last but not least, Mel Schreier, who is on our emeritus board. So they will all be there at the reception. We hope you'll join us. They have ribbons to distinguish who they are, and the networking reception will be on the 3rd floor in the roof garden. So we hope to see you there. Thank you.
Thank you to the board members. I'm glad that was all of you, because I was really worried we were going to just turn into the entire audience. And thank you all for coming, but mostly I would like to thank Professor Green for taking the time to talk to us. Once more, Professor Green.
Thank you.